Welcome to the section 14 of the course of Dispersed Systems with C++ and Qt. Now we are going to implement the compile function for our RPN syntax analyzer. The principal purpose of the compile function is to process the operations of a set of rules. Just remember, a rule can be one of these. I want to this by to RPN. For illustration, I will write down the infix version. You can test it later, but the first step is going to create this operation, and then this one, and later this one, and at the end all the result of all this process will be with addition with the 5 of the beginning. So this is just for illustration. Okay, so the compile function determines whether a rule has a good RPN syntax or not. Advancing the analysis of this function, all we need to do is to first create a local stack to hold the elements. Second, determine the different errors that may appear. Remember that a good compiler should always expose errors with a description. Third, the compiler needs to determine the type of the element. It means it is a ID, operator, end of line, end of file, and so on. Fourth, the process of compilation is creates all the operations that the rules until there is no element left, or maybe there is an error. So let's start. Let's go to the .pp, and I'm going to include some headers that maybe that are important, can be important. Q stack, Q the okay. This we're going to define a loop, in the function. To get signals of the compiler will give those signals might be errors or that the compilation was successful. So let's first create the RPN syntax analyzer compile. Oops. So then we need a while. But for this while, and okay, correct. So now we should declare the stack and the sign table to determine when we finish to analyze all the rules. So Q stack, it's okay to be a variable, so it's all build their stack. Something I like to do is to ensure that it's clean. It's not necessary, but it's something that I usually do. And then Q string find on table, and we know that it's 6 elements. Let me just write it down to you to understand it how much. So the first one, that its value 0 is success. Not enough parameters for the second element, and not implemented operator. valid symbol and of all font and unexpected error. Then that's it. Okay, so now inside the while we need to determine the type of the lexems to process operation. Doing so, we are going to create a switch. First of all, remember lexical analyzer, it's a pointer. So we're going to have a token from the file, and then type. We're going to handle all the cases that are ID, operator, end of file, error, open bracket, close bracket, and unexpected error. That's default. So it's RPN lex analyzer, lexem, ID, break. Case lex analyzer, lexem, operator, break. Case lex analyzer, lexem, end of file, and break. Lex analyzer, lexem, other open bracket, break. Case lex analyzer, lexem, close bracket, break. Case I think that there is no default, the break. Great. So in the ID we built add an element and put the stack, as simple as that. So from the builder, push to builder, I need to build an atom node with the token, specific token, and break. That's it. Well, in the operations, first we need to verify if we have at least 2 elements in the stack to do the operation, and also remember that we have a negation operation and it only needs 1 operand. So let's verify that. So if builder builder dot size equal to greater or equal to all in this token different to exclamation. Okay. Entonces write equal builder stack pop int left stack dot. So what's the reason that we are going to have the right first and then the left? Let me see. Just let's remember that we have this operation, and so this is the beginning of the stack, and this is where there is the top. This is the bottom of the stack, better words to understand it. So we have an operation that is a subtraction. So it's different, it's different to do this, to do this. So we have to, how do you say it? we have to make sure to ensure that we're doing it's not associative. For example, the subtraction is not associative. It's very different, and we need to ensure that this operation is correct. So, for example, we might say that this is the left and this is the right. So let's see. The operation subtraction is first, then it's the left, then it's the right, and we are going to respect the order of the operation by this way, saying that this is the left and this is the right, and it's better to clarify to the programmer, not be confused, because sometimes with some words maybe we can say A and B, but it's very abstract and it may confuse you, and it ranges for errors in the coding. So hope this is clear for you. So the next step is to, inside of this if, we're going to determine all the binaries operations. So let's start it with L dot M stack for the implication that it's an arrow, and we are just push the operation to the stack dot I always forget it, push PTB and if, and then left and right. This is the reason that it's very important to make sure that it's the left and the right. Also if L dot M token to the disjunction, same stuff, but I like to write it, push BTB dispute or operation left that right. Also if L dot M as token to conjunction the user stack dot push TB and left right. Okay, and the last one is else. This is for the implication. It's the same, pretty much the same. TB left, right, and that's it for now. Okay, seems correct. So then for the unary, this is for the binary if up if. For the unary functions, that it's only the negation. We need to determine that at least there is an element in the stack. So let's do it. Else if of builder stack dot size greater or equal to 1, and let's sure that it's the negation. Great. So int left equal build stack, pretty much the same as the other one, but only one operand TB not, and it's the left. That's the first one in the stack. And okay, I scroll down here because I can do builder stack Okay, so else, if any of these cases is approached, and then we don't have any operation to do it, so this means that we are having an error. So we're going to change the value of signal to 0, 1, 2 equal 2. Great. So for the proof analyzer operation, that's it. So now let's handle the errors. And if we found end of file an error, I think that I forgot the error here. Could we also have a case proof analyzer lexem error break? Then we need to handle it with this table that we have here. So we just need to assign the signer variable to these values. So it's pretty simple. So I know I know already the value, so I just wanted to tip it. And signal equal 1. And okay, for the parentheses we don't handle them, so we can put in the default. The default means that it's a unrecognizable lexem. We don't have any idea what is this or what is that. So for example, open brackets and close brackets, because RPN doesn't have brackets, then we are going to put as a default, and it's pretty simple. It simplifies all this code, and that's it. So and switch and voila. Okay. The last part, determine if the compiler was successful or not. So with by these signals, we're going to determine if the compiler was correctly compiled. So if we reach the end of file and there is only one element in the stack, means that the compilation was successful, because it means that there is no mismatch in the operations and no errors. So for example, remember that we have 5, 1, 2 plus 4, multiplication 3 minus and plus. The result, the output of all this process may be just one element. That it's the result. It's like putting a signal or equal in the stack. That it means that there is only an element. We have successfully do the compilation, and try it. Make some analysis with this. If you put another operation, what's going to happen, or if you put more elements, more IDs, what's going to happen, and just make some analysis with that. And if you have any comment, put it in the comment section of YouTube or in the blog. Okay. So, and the way that we're going to determine if the compilation was successful is to and signal 4. What means 4? 0, 1, 2, 3, 4. End of file found. As I say, we reach the end of file, and the builder stack has only one element. Return true. Else if not, there is an error. Error appears. So and the signal in the file, but there is some more elements in the stack. we're going to find there is an expected error. Yeah, unexpected error. So we're going to put in the application output something to describe what happened. I want to do it signal and no and offline and return false. So that's it for this function. It was pretty simple, but just hold on. I think that we can optimize this function. First of all, we already changed the names because we need to determine if the variable is local and what type it is. That's pretty simple. And we also can put this table as cons. Optimization. And also because the function is not modifying any member of the class, we can put a cons and ensure that it won't change anything. It's just a good practice of C++. So cons, and we also need to put here cons. Let's compile and pray that anything is incorrect. Great. What is it? Missing template argument. Oh, it isn't int. I think there is an int. Yes, it's int. Oh, sorry. Pretty basic. Great. So that's it, guys. This is the end of this video. So hope you enjoy it. Leave a comment if you like to do it, and share with your friends if you want. In the next video, we're going to implement the infix syntax analyzer. That it's a harder class. There is no comparison with this compile function and the other one. The other one is very complex. So basically, you're going to see in the next video. So thank you and see you later.